Imagine casting a pebble into an ocean so vast its furthest shores lie beyond any conceivable horizon. The ripples spread, but what lies beyond their reach? What lies beyond the water itself? Now, consider that pebble as our entire observable universe. Everything we have ever seen, every galaxy, every star, every atom, all contained within a cosmic sphere roughly 93 billion light-years across. But what if this isn't the universe? What if it's merely a single, isolated bubble in an unimaginable ocean of other realities? Just beyond the reach of our most powerful telescopes, past the very edge of the light that has had time to reach us, lies an expanse that defies observation. A cosmic frontier where our established laws might bend, break, or simply cease to exist, giving way to new dimensions, new physics, and perhaps other Big Bangs. This isn't merely philosophical musing. The question of what lies beyond our observable cosmos carries profound implications. It challenges the very foundation of our existence, forcing us to confront whether our finely tuned universe is a cosmic accident, a design, or simply one of countless experiments playing out in an infinite laboratory. It asks if the fundamental rules that govern our reality are universal, or just local parameters in a cosmic tapestry woven with diverse threads. In this documentary, we will embark on an intellectual expedition to the limits of scientific imagination. We will dissect the leading hypotheses, from an infinitely stretching homogeneous void to the teeming landscapes of the multiverse, where bubble universes drift through an eternal inflation. We will confront the radical ideas of brain cosmology, where our universe is but a membrane in a higher dimension, and delve into the quantum realm where every choice branches reality into countless parallel worlds. Each theory offers a glimpse into a cosmos far stranger and more expansive than we could ever conceive. If you are ready to venture into the deepest mysteries of existence, then hit that like button, subscribe to Terran, and join us on this extraordinary journey. The greatest revelations often lie just beyond the edge of what we can see. Let's begin. Our journey into the cosmic beyond must begin with a clear understanding of our current vantage point, the observable universe. It is a concept often misunderstood, frequently conflated with the entirety of existence. Yet, this observable universe is not a physical boundary in space, but a horizon defined by time and the fundamental speed limit of light. It represents the spherical region of space-time from which light has had sufficient time to reach Earth since the Big Bang. Imagine standing in the middle of a colossal ancient forest. You can only see as far as the light from the oldest trees has travelled to your eyes. Beyond that, the forest stretches on, unseen, but undoubtedly there. The current diameter of this cosmic sphere is approximately 93 billion light-years, a figure that often surprises, given the universe's age of 13.8 billion years. This dramatic discrepancy arises from the continuous expansion of space itself. While a photon may have travelled for 13.8 billion years to reach us, the space it traversed has stretched and inflated during its journey, carrying its origin point much further away than its initial light travel distance would suggest. It's akin to an ant crawling across an inflating balloon. The distance covered on the surface is only part of the story, as the balloon's expansion also contributes to the increasing separation from its starting point. This expansion continually pushes the effective edge of what we can ever hope to see. At the very limit of our vision lies the cosmic microwave background, or CMB. This ancient light, detected uniformly across the sky, is a faint afterglow from when the universe was only 380,000 years old, a time when it finally cooled enough for photons to travel freely through space. Before this epoch, the universe was an opaque, scorching plasma, trapping light within its dense embrace. The CMB is literally the baby picture of our universe, an evidentiary exhibit of its earliest moments, and it forms the ultimate physical wall of our observable cosmos. No information, no light, no signal of any kind from before. The CMB can ever reach us directly, regardless of how advanced our technology becomes. It is a fundamental barrier built into the very fabric of space-time. This brings us to a crucial distinction: the difference between the universe and the observable universe. The observable universe is a personal bubble, a unique sphere centered precisely on us. If an alien civilization existed billions of light years away, they would have their own observable universe, a sphere of similar size, but encompassing a different set of galaxies and regions of space. While their observable bubble would overlap significantly with ours, there would also be vast portions of their observable cosmos that are utterly invisible to us, and vice versa. This means that even if the entire universe is finite, it is almost certainly far larger than the tiny fraction we can currently perceive. The cosmological principle, which states that the universe is homogeneous and isotropic on large scales, supports this idea. Our location is not special, and thus, the universe must extend far beyond our current sight. The sheer scale of this unseen domain is staggering. For every galaxy we detect, there are untold numbers beyond the horizon, existing in real, physical space, just not yet in our light cone. This isn't mere speculation. It's a logical deduction from the Big Bang theory and the finite speed of light. The observable universe continues to grow slightly larger each moment, as light from ever more distant regions finally arrives, but it will never encompass the entire universe if the universe itself is truly infinite, or even just vastly larger than our bubble. Our telescopes are essentially time machines, allowing us to peer into the past, but the further back in time we look, the further away in space those ancient photons originated. Until we hit the ultimate barrier of the CMB, the existence of this unobservable realm immediately ignites profound questions. If space stretches indefinitely beyond our horizon, what form does it take? Does it continue with the same fundamental laws, the same types of particles, the same cosmic structures we see here? Or do the rules of physics themselves undergo transformations, morphing into exotic realities where gravity behaves differently, or where the very dimensions of space vary? Without direct observation, we are forced to turn to theoretical physics, to the most audacious hypotheses that attempt to chart these uncharted waters. Our current understanding of cosmology, while robust within our observable bubble, might be just a single chapter in an unimaginably vast cosmic epic. The limitation of the observable universe is not a defeat for science. It is a fertile ground for new ideas. It is the definitive boundary that forces us to ask, what could possibly lie beyond? This question is more than academic. It touches upon the very nature of reality, the origin of our universe, and whether our existence is a singular cosmic event or one of an infinite multitude. We are about to explore the boldest scientific answers to this question, starting with the most straightforward, yet still profoundly unsettling possibility: an endless, uniform cosmos. While our observable universe defines the cosmic sphere from which light has had time to reach us, it is a crucial scientific understanding that this boundary does not necessarily define the entirety of the universe. Indeed, the simplest and arguably most widely accepted hypothesis for what lies beyond this horizon is a vast, potentially infinite expanse of space-time that simply continues, endlessly, with more of the same fundamental reality we perceive. This concept, often called the infinite emptiness, or the level Y multiverse by physicist Max Tegmark, is less a radical departure from our current understanding and more a logical extrapolation of observed cosmological data. The foundation for this idea rests heavily on the geometry of our universe. Modern cosmological observations, particularly those from the Planck satellite, mapping the cosmic microwave background, reveal that our universe is remarkably flat. This isn't flat in the sense of a two-dimensional surface, but rather in its spatial curvature. Imagine the difference between a saddle-shaped universe, negative curvature, a spherical universe, positive curvature, or a truly flat one. A flat universe within the bounds of observational error implies that it is either infinite in extent or at least so incredibly vast that its curvature is undetectable over the scales we can observe. If the universe truly extends indefinitely, then our observable bubble is merely a small local patch within a much grander, unbounded cosmos. In this infinite expanse, the laws of physics, the fundamental constants, and the very composition of matter and energy are presumed to be identical to our own. This isn't a realm of exotic physics or different dimensions. It's simply more universe. You would find galaxies, galaxy clusters, vast cosmic filaments, and enormous voids, all structured according to the same cosmic web patterns we observe. The dark matter and dark energy that dominate our local region would continue to exert their influence, maintaining the same delicate balance that shapes our familiar cosmos. It's a universe that, if we could somehow instantly teleport billions of light years beyond our horizon, would look, statistically speaking, much like our own. The profound implications arise from sheer scale and the mathematics of probability. If the universe is indeed infinite in extent, and if the number of possible arrangements of particles within any given finite volume, like our observable universe, is also finite, albeit an astronomically large number, then by definition, every possible arrangement must eventually repeat. This is not a matter of philosophical conjecture, but a statistical inevitability. Somewhere, unimaginably far away in this boundless cosmos, there must be another region of space identical to our observable universe, down to the last subatomic particle. This means, chillingly, that there is another Earth, another you, reading this very sentence, and countless variations of your life unfolding across this cosmic canvas. The distances involved are not merely vast, they are truly incomprehensible. To find a precise replica of your observable universe, with every quantum state mirrored, the numbers involved would stretch beyond a Googleplex light years, a 1 followed by a Google zeros. This is not a distance we could ever hope to traverse, nor one whose light could ever reach us within the lifetime of the universe. Yet, the mathematical framework suggests their existence, not as parallel universes in a different dimension, but as spatially separated regions within the same infinitely stretching reality. They are not beyond our universe, but simply beyond our observable portion of it. This infinite repetition perspective means that every possible outcome that could have unfolded in your life has indeed happened an infinite number of times in these distant, identical universes. Every decision you could have made, every path not taken, exists as a tangible reality for a version of yourself. This thought experiment fundamentally challenges our concept of uniqueness and destiny, replacing it with an almost overwhelming sense of cosmic redundancy. Our universe is not a unique snowflake, but one of an infinite number of identical snowflakes, scattered across an endless winter landscape. While compelling, this hypothesis offers no direct observational evidence due to the very nature of its premise. What lies beyond the observable horizon is, by definition, unobservable. We can only infer its existence through the internal consistency of our cosmological models and the observed flatness of space. The theoretical possibility of spatial infinity is supported by the theory of cosmic inflation, which posits an extremely rapid expansion of the early universe that would have stretched any initial curvature out to scales far larger than our observable universe. If inflation is correct and continued long enough, it would naturally lead to a universe that appears flat and is, in all practical terms, infinite. However, the question remains, does this infinite expanse truly continue with the same physics, or do the rules begin to change in ways we cannot predict? The Level 1 multiverse describes a universe that is homogeneous and isotropic, on scales far beyond our horizon. A universe that is simply more of the same. But what if the very mechanisms that generate these vast regions are themselves more dynamic and creative, leading to realities with entirely different fundamental properties? This is where the simple elegance of infinite emptiness gives way to far more complex and mind-bending propositions, hinting at universes where the very fabric of existence is rewritten. This takes us from merely extending our current reality to entirely new forms of cosmic architecture, challenging us to consider if our universe is truly just one of an infinite array of bubbles, each playing by its own set of rules. If the infinite expanse of a uniform universe with its endless repetitions seems mind-bending, then prepare to delve into a concept that pushes the boundaries of reality even further: eternal inflation. This theory, a powerful extension of the inflationary paradigm, posits that the process which created our universe's initial exponential growth may never truly end. Instead, it continues indefinitely, constantly spawning new bubble universes from its ever-expanding primordial foam. This is not just more of our universe, it's the genesis of other universes, each potentially distinct. To grasp eternal inflation, we must first revisit the standard theory of cosmic inflation. Proposed in the early 1980s by physicists like Alan Guth and Andre Linde, inflation explains several puzzling features of the Big Bang model, such as the flatness of space, the smoothness of the cosmic microwave background, and the absence of magnetic monopoles. It suggests that in the first tiny fraction of a second after the Big Bang, roughly between 10^36 and 10^32 seconds, the universe underwent an extraordinary period of exponential expansion, stretching far beyond what ordinary expansion could achieve. This rapid burst was driven by a hypothetical energy field, often called the inflaton field. Under the standard model of inflation, this inflaton field eventually decayed, releasing its energy and reheating the universe, thus setting the stage for the hot, dense Big Bang we observe. Our observable universe emerged from one such region where inflation ended. However, the concept of eternal inflation arises from the realization that if the inflaton field's quantum fluctuations are sufficiently large, it may not decay uniformly across all of space. Instead, in some regions the field might reinflate, perpetuating the exponential expansion, while in others it might decay, forming a new bubble universe. Picture a vast cosmic foam. Within this foam, some regions are still undergoing rapid exponential inflation, stretching spacetime at an incomprehensible rate. These are the inflating patches, but occasionally pockets within this inflating sea bubble off. In these bubbles, the inflaton field decays, releasing its energy, and the local expansion slows down dramatically, giving birth to a new, distinct universe, a pocket universe. Our own observable universe, then, would be just one such pocket, a minuscule island of settled reality in a sea of unending, chaotic inflation. The crucial difference from the Level 1 multiverse is that these bubble universes are not merely spatially separated regions of the same continuous spacetime. They are causally disconnected. The space between them is inflating so rapidly that light, or any information, can never travel from one bubble to another. Each bubble forms its own self-contained spacetime, its own universe, in every meaningful sense, governed by its own localized Big Bang and its subsequent evolution. This is what Max Tegmark classifies as a Level 2 multiverse. The implications of eternal inflation are staggering. If the process truly is eternal, then an infinite number of such bubble universes must have been, and continue to be, spawned. Each bubble could potentially have different initial conditions, different properties of the inflaton field, and crucially, different ways the field decays. This means that the physical constants we observe in our universe, the speed of light, the strength of gravity, the mass of an electron, might not be universal laws but rather local settings within our particular bubble. Consider the vast array of possibilities. One bubble universe might have a slightly stronger gravitational constant, leading to stars that burn out much faster. Another might have different fundamental particle masses, preventing the formation of stable atoms. Yet another could have more spatial dimensions, or even different types of dark energy. The very existence of such a diversity of universes elegantly addresses the fine-tuning problem. A perplexing observation that our universe's constants seem precisely calibrated for the emergence of life. If there are infinitely many universes with varying parameters, then it's no longer surprising that we find ourselves in one that supports life. It's simply a selection effect. We couldn't exist to observe any of the others. The concept of eternal inflation is a direct consequence of quantum field theory in the context of general relativity. Quantum fluctuations are inherent to quantum fields, and the inflaton field is no exception. These fluctuations can, in certain models, prevent inflation from ending everywhere simultaneously. Instead, they kick some regions of the field back up to higher energy states, causing them to reinflate while others transition to the end state. This creates a fractal-like structure where inflation never truly ceases, generating an endless succession of new Big Bangs. The scientific evidence for eternal inflation is indirect but powerful. It arises naturally from many viable models of inflation. While we cannot directly observe these other bubbles due to their causal disconnection, the theory's ability to explain several cosmological puzzles makes it a compelling, if unsettling, hypothesis. It transforms our singular universe into a single leaf on an infinite, ever-growing cosmic tree, each leaf representing a universe with its own unique history and physical laws. This paradigm shift forces us to re-evaluate what the universe truly means. It moves beyond the idea of a single, all-encompassing reality to a grander, multiversal framework. Our Big Bang, once seen as the absolute beginning of everything, becomes a local event, a birth pang in a much larger ongoing cosmic saga. The space between these bubbles is not empty. It is a perpetually inflating void, a dynamic sea of energy continuously giving rise to new realities. This is the Level 2 multiverse, a universe of universes, each a distinct cosmic experiment. And yet, even this sprawling concept may only scratch the surface of reality's ultimate complexity. Let us begin our deep dive into the multiverse with Max Tegmark's classification, which provides a useful framework for understanding the various forms other universes might take. We start with the Level 1 multiverse, a concept so straightforward it almost escapes immediate recognition as a distinct multiverse at all. Yet its implications are profoundly unsettling. It is, in essence, the logical conclusion of an infinitely large universe, one that simply extends far beyond our observable horizon, continuing with the same fundamental laws and particles we experience in our cosmic neighbourhood. As we discussed, the observed flatness of our universe, supported by precision measurements from missions like the Planck satellite, strongly suggests that space is either infinite or so vast that its curvature is undetectable. If this holds true, and space stretches out indefinitely in all directions, then the Level 1 multiverse becomes an undeniable mathematical certainty. Our observable universe, a sphere approximately 93 billion light-years in diameter, is but a finite patch within this boundless expanse. The unobservable regions beyond our cosmic horizon are not fundamentally different. They are simply too far for light from their earliest moments to have reached us yet. The universe, in this model, is a colossal, uniform canvas upon which the same cosmic drama unfolds endlessly. Gravity, electromagnetism, the strong and weak nuclear forces all operate with identical strengths. The fundamental particles, from quarks to electrons, have the same masses and properties. Stars ignite, galaxies form, and cosmic structures evolve following the same principles established in our astronomy textbooks. There is no exotic physics here, just more of the familiar cosmos. The true mind-bending aspect of the Level 1 multiverse emerges when we consider the implications of infinity combined with the finite nature of particle arrangements. While the universe may be infinite in space, the number of distinct ways that particles can arrange themselves within any finite volume, like a sphere the size of our observable universe, is finite, albeit an astronomical figure, a number so enormous it dwarfs even the total number of particles in our entire observable cosmos. However, in an infinite universe, every possible configuration of particles, every quantum state, every specific arrangement of matter and energy must eventually repeat an infinite number of times. This means that somewhere out there, at an unimaginable distance, there exists another region of space identical to our own, down to the last atom, down to the last quantum fluctuation. In that mirror cosmos, there is another Earth, another Milky Way, another you, not just a near-identical copy, but an exact duplicate, living out the same life you are experiencing at this very moment. Beyond that, there are infinite other copies, each perhaps slightly different, representing every possible choice you could have ever made. Every fork in the road of your personal history. The distances to these doppelganger universes are staggering. Max Tegmark estimates that a twin Earth might lie roughly 10 to 29 meters away, a number so large that writing it out would consume more ink than there are atoms in our observable universe. To find a truly identical copy of our entire observable universe, the distance would be even more mind-boggling, perhaps 10 to 10⁻⁻18 meters away. These are not distances that can ever be traversed or whose light could ever reach us, even given infinite time. They exist in our shared reality, yet remain forever beyond our observational grasp, a testament to the sheer scale of the cosmos. This concept challenges our cherished notion of individuality and uniqueness. If every possible arrangement of matter is repeated infinitely, then every person who has ever lived, every historical event, every artistic creation, has an infinite number of identical counterparts scattered throughout this boundless cosmic expanse. Our universe, in this view, is not a unique masterpiece, but one of an infinite series of identical prints from the same cosmic plate. The Level 1 multiverse also provides a straightforward, if often overlooked, answer to questions about what lies beyond our observable horizon. It doesn't invoke new physics or alternate dimensions. It simply asserts that the universe continues. The cosmic structures we observe, the cosmic web of galaxies and voids, are simply extended indefinitely. There is no edge in the conventional sense, just a continuously expanding tapestry of space-time. While mathematically compelling, the untestability of this hypothesis poses a challenge for empirical science. We can never hope to send a probe to verify the existence of these distant copies, nor can we detect any signal from them. Our belief in the leveler multiverse rests on the assumption of an infinite universe and the statistical inevitability of repetition. This places it on a different footing than theories that might offer testable predictions. However, its simplicity and direct extrapolation from our best cosmological models make it a powerful, foundational concept in the broader multiverse discussion. It forces us to ponder the very meaning of existence and uniqueness. Is our specific universe, our specific life, truly special if identical versions are playing out infinitely often elsewhere? Or does the sheer scale of such a cosmos diminish the value of any single instance? This intellectual and philosophical weight, stemming from a seemingly simple extrapolation of flatness and infinity, lays the groundwork for even more radical multiversal proposals where not just arrangements, but the very laws of physics themselves vary across cosmic realms. These are the realms of Level 2 multiverse theories, where the concept of universe truly splinters into fundamentally different realities. If the Level 1 multiverse posits an infinite repetition of our reality, the Level 2 multiverse introduces a far more profound and unsettling concept: universes where the very laws of physics are different. This isn't just about variations in particle arrangements. It's about fundamentally alien realities where the speed of light might be slower, gravity might be repulsive, or atoms themselves might not be able to form. This radical departure from our familiar cosmos arises primarily from the theory of eternal inflation, which we previously explored as a mechanism for generating an endless stream of bubble universes. Recall that eternal inflation suggests that the universe, on a grander scale, is a perpetually inflating void that continuously spawns new pocket universes when the inflaton field locally decays. The critical distinction here is that these separate bubble universes are causally disconnected. The space between them expands so rapidly that light can never bridge the gap, meaning each bubble evolves as an independent entity, entirely cut off from its cosmic siblings. This isolation is key to allowing their fundamental properties to diverge. The variations in physical laws within these Level 2 universes stem from the diverse ways the inflaton field can decay, or from different regions of the inflating cosmos having inherently different energy landscapes. Imagine a landscape with many valleys of varying depths. Our universe might have settled into one such valley, determining its specific set of physical constants. Other bubbles, however, could have settled into different valleys, each corresponding to a unique set of fundamental parameters. These parameters include the masses of elementary particles, the strength of the fundamental forces, like electromagnetism and the strong nuclear force, the value of the cosmological constant which drives dark energy, and even the number of spatial dimensions. Consider the dramatic implications of such variations. In one universe, the electron might be significantly heavier, rendering stable atoms impossible. In another, the strong nuclear force, which binds protons and neutrons together, could be weaker, preventing the formation of atomic nuclei beyond hydrogen. The cosmological constant, a crucial factor in our universe's expansion, could be orders of magnitude larger in a different bubble, causing space to expand so rapidly that galaxies never form, or so small that the universe collapses almost immediately after its birth. These are not minor tweaks. They are fundamental alterations that would create entirely unrecognizable realities, utterly inhospitable to life as we know it. This inherent diversity within the Level 2 multiverse offers a powerful, albeit controversial explanation for the apparent fine-tuning of our own universe. The constants of physics in our cosmos seem almost miraculously tailored for the existence of stars, galaxies, and life. For instance, if the strong nuclear force were just a few % stronger or weaker, carbon-based life would be impossible. If the cosmological constant were even slightly different, the universe would either have expanded too quickly for structures to form or collapse before life could emerge. Such precise calibration often leads to questions about design or extreme cosmic luck. The Level 2 multiverse, however, offers a statistical solution. If an infinite number of universes exist, each with a random assortment of physical constants, then it becomes inevitable that some of them will have the precise conditions necessary for life to arise. We, as observers, naturally find ourselves in one of these rare, life-permitting universes. It's an anthropic selection effect. We can only exist and observe a universe that allows for our existence. This perspective shifts the question from why is our universe so special to, given an infinite array of possibilities, it's not surprising that we're in one of the habitable ones. The concept is further bolstered by theories like string theory, which predict an enormous number of possible vacua or stable states for the universe, each corresponding to a different set of physical laws. This landscape of possibilities, often estimated to be around 10,500 different stable configurations, perfectly complements the idea of eternal inflation. The inflating field, as it decays in different regions, could fall into different valleys in this landscape, thereby imprinting distinct physical laws onto each nascent bubble universe. While profoundly elegant in its ability to address cosmological puzzles, the Level 2 multiverse faces the same fundamental challenge as its Level 1 counterpart: direct observability. By definition, these other universes are causally disconnected, meaning no information, no light, no gravitational wave can ever travel from them to us. Our only evidence for their existence comes from the theoretical robustness of the eternal inflation model itself and its capacity to explain cosmic fine-tuning. However, some theoretical physicists are exploring indirect signatures. Could a collision between our universe and another bubble leave a subtle imprint on the cosmic microwave background? Perhaps a statistical anomaly or a cold spot that can't be explained by standard cosmology. Such an event, though rare and challenging to model, could provide a tantalizing, albeit faint, whisper from an adjacent reality. These investigations remain highly speculative, but represent humanity's ambitious attempt to find empirical traces of these otherwise hidden realms. The Level 2 multiverse fundamentally transforms our perspective on cosmic uniqueness. Our universe is no longer the sole stage upon which reality unfolds, but one play in an infinite cosmic repertory. The laws we take for granted, the forces that sculpt our galaxies and bind our atoms, are revealed as potentially local manifestations, not absolute truths across all existence. This paradigm opens up a dizzying array of possibilities, forcing us to reconsider the very definition of what is possible and what is real. But even the vastness of Level 2 pales in comparison to even more exotic constructs, where our universe is not a bubble, but a membrane, a mere slice of reality floating in higher dimensions. Beyond the infinite repetitions and varying physical laws of the Level 1 and 2 multiverses lies an even more mind-bending concept, one that originates from the deepest frontiers of theoretical physics, the brain-world hypothesis. This idea, deeply rooted in string theory, and its more encompassing successor, M-theory, suggests that our entire universe, with its 3 spatial dimensions and 1 time dimension, might not be all there is. Instead, our reality could be confined to a giant cosmic membrane, or brain, floating within a higher dimensional space called the bulk. To appreciate the brain world, we must first briefly touch upon its progenitor, string theory. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating one-dimensional strings. The different vibrational modes of these strings correspond to different particles, much like different notes played on a violin string. A key and often unsettling prediction of string theory is that the universe must possess more than the familiar 3 spatial dimensions. Most versions require 10 or 11 dimensions for mathematical consistency. For decades, physicists grappled with the question of why we only perceive 3 spatial dimensions. String theorists propose that the extra dimensions are compactified, curled up into incredibly tiny, unobservable loops at every point in space, far too small for our most sensitive instruments to detect. However, the brain-world hypothesis offers an alternative, more radical solution. The extra dimensions are not necessarily compactified, but rather we are confined to a lower dimensional surface within them. Imagine a 2-dimensional sheet of paper floating in a 3-dimensional room. Creatures living on, the paper could only perceive two dimensions, length and width, even though their entire world is embedded in a larger, higher dimensional space. In the brain world scenario, our universe is analogous to that sheet of paper, a three-dimensional brain existing within a larger, often much larger bulk space that contains additional spatial dimensions. These extra dimensions are not curled up. They are large, potentially infinite, but we cannot move or perceive them directly. The crucial element of the brain world hypothesis is how fundamental forces behave within this structure. It suggests that while the strong nuclear force, the weak nuclear force, and electromagnetism are all confined to our brain, gravity is different. Gravity, according to this theory, is able to leak or propagate into the higher dimensional bulk. This distinction is incredibly important because it could explain one of the greatest mysteries in physics, the weakness of gravity compared to the other fundamental forces. Consider two magnets. They are easily strong enough to pick up a paperclip against the entire gravitational pull of the Earth. Why is gravity so incredibly feeble in comparison? In the brain world model, gravity appears weak to us precisely because its influence is diluted by spreading out into the extra dimensions of the bulk. While the other forces are trapped on our brain, gravity's energy and effect dissipate across the larger space, making it seem much weaker from our 3D perspective. This elegantly addresses the hierarchy problem, the enormous discrepancy between the gravitational scale and the electro-weak scale, the energy scale at which electromagnetism and the weak force unify. If gravity is spread across many dimensions, then its true strength in the higher dimensional bulk could be comparable to the other forces, but it appears diminished to us because we only experience a fraction of its total influence on our brain. The existence of a bulk space, filled with extra dimensions and potentially other brains, opens up the possibility of an entirely different kind of multiverse. Our universe is not just one bubble among many, but one membrane among many. There could be other parallel brains, other universes, also floating within the same bulk. These brains could be incredibly close to ours, separated by only a tiny distance in the extra dimensions, yet remain invisible and undetectable to us because our light and matter are confined to our own brain. These parallel brains could have entirely different properties. They might have different fundamental constants, different particle content, or even different numbers of dimensions if their brains are themselves of different dimensionality. What's more, these brains might not be static. They could move, interact, and even collide within the bulk. Such a collision could be a cataclysmic event, potentially triggering a new Big Bang, or even causing the end of our universe as we know it. This dynamic interaction forms the basis for some cyclic multiverse models, which we will explore further. Finding evidence for the brain world hypothesis is one of the most challenging yet exciting quests in theoretical physics. If extra dimensions exist, even if we cannot enter them, they might leave subtle imprints on our brain. For instance, tiny deviations from Newton's law of gravity at very small distances could be a hint that gravity is beginning to feel the presence of these extra dimensions. Experiments at particle accelerators like the Large Hadron Collider could also search for particles that might escape into the bulk or signals that hint at the presence of higher dimensions. The detection of mini black holes or other exotic phenomena could be a smoking gun for extra dimensions. The brain world concept transforms our perception of cosmic isolation. We might not be alone in a vast empty space, but merely separated by an imperceptible veil from countless other realities, existing just next door in a higher dimension. This profound idea, born from the mathematical necessities of string theory, offers a tantalizing glimpse into a universe far more intricate and interwoven than our current three-dimensional perspective allows. It raises the possibility that the very fabric of our cosmos is a surface, a cosmic drumhead, vibrating with the echoes of other worlds, other realities just beyond our reach. If our universe is indeed a brain floating in a higher dimensional bulk, then the possibilities for cosmic interaction become truly revolutionary. This leads us to the concept of colliding realities and the fascinating yet deeply speculative cyclic multiverse hypothesis. This theory posits that our Big Bang wasn't a singular ultimate beginning, but merely one event in an eternal cycle of cosmic creation and destruction, potentially triggered by the violent collision of brains. For decades, The standard cosmological model described the Big Bang as the singular moment of creation, an ultimate beginning from which all of space-time, matter and energy emerged. But the idea of a universe spontaneously appearing from nothing has always troubled physicists and philosophers alike. The cyclic model offers an elegant, if radical, alternative. What if the universe doesn't begin and end, but rather endlessly recycles itself? The most prominent version of the cyclic multiverse hypothesis, often called the ekpyrotic model, from the Greek word ekpyrosis meaning conflagration, draws directly from brain cosmology. In this scenario, our universe is a three-dimensional brain, and it exists parallel to at least one other partner brain within a higher dimensional bulk. These brains are not fixed but are in constant, albeit incredibly slow motion. Over quadrillions of years, these brains gradually drift towards each other. Imagine two colossal invisible sheets, slowly moving closer in a dimension we cannot perceive. As they approach, a subtle gravitational attraction begins to pull them together, eventually leading to a cataclysmic collision. This collision, in the ekpyrotic model, is the Big Bang. The immense energy released from the impact generates all the matter, energy and radiation we observe in our universe, restarting the cosmic clock. It's a universe born not from a singularity, but from an interdimensional crash. Following the collision, the brains might momentarily stick together or bounce apart, beginning a new phase of expansion. Our current universe, then, would be in such an expansion phase, cooling and forming galaxies as it stretches. But this expansion is not eternal in the cyclic model. Eventually, gravity, perhaps with the aid of a decaying dark energy or some other mechanism, would overcome the expansion, causing the universe to contract. This cosmic contraction, a big crunch, would bring the brains back together for another collision, restarting the cycle. This offers several compelling advantages over the standard Big Bang model. Firstly, it elegantly avoids the initial singularity problem, where the universe originates from an infinitely dense, infinitely hot point, a state that breaks the laws of physics. Instead, the universe always exists, simply transitioning between phases of contraction and expansion, with the Big Bang being a violent yet finite event. Secondly, it provides a natural mechanism for resetting initial conditions and potentially smoothing out any irregularities, addressing some of the challenges that inflation was designed to solve. The time frame for a full cycle in these models is truly immense, dwarfing the 13.8 billion years of our current universe. We're talking about quadrillions or even quintillions of years for a complete expansion and contraction phase. This means that if the cyclic model is correct, our universe has likely experienced countless Big Bangs and Big Crunches before our current iteration, and will experience countless more in the unfathomably distant future. Each cycle could potentially begin with slightly different parameters, leading to a level 2 type of multiverse over cosmic time. However, the cyclic model faces significant theoretical and observational challenges. One major hurdle is the entropy problem. Each cycle of contraction and expansion would theoretically increase the entropy of the universe. If the universe repeatedly undergoes cycles, entropy should accumulate, meaning each subsequent cycle would be messier than the last. This would lead to an eventual heat death, breaking the eternal nature of the cycles unless there's a mechanism to reset or reduce entropy at the end of each cycle. Modern variations of the ekpyrotic model have proposed solutions to this, often involving exotic physics in the bulk dimensions or mechanisms that effectively dilute entropy between cycles. Another challenge comes from the observational evidence for cosmic acceleration, driven by dark energy. Our universe is not slowing down towards a big crunch, it is speeding up. For a cyclic model to work, dark energy would need to be a transient phenomenon, eventually decaying or reversing its repulsive effect to allow for contraction. If dark energy is truly a cosmological constant as current data suggest, then a big crunch and subsequent collision become impossible, leading to a universe that expands forever into a cold, empty future. Despite these challenges, researchers like Paul Steinhardt and Neil Turok have continued to refine ekpyrotic and cyclic models, exploring how they could be made consistent with observations. They propose that dark energy might be a phase of matter that only temporarily dominates, eventually giving way to other forces, or perhaps the collision itself could be a more nuanced interaction than a direct bang, allowing for a more graceful rebound. The search for observational signatures of a cyclic universe is ongoing. While direct observation of a colliding brane is impossible, the theory predicts specific patterns of gravitational waves that could be detectable, or subtle deviations in the cosmic microwave background that differ from standard inflationary models. For instance, the ekpyrotic model predicts a different spectrum of primordial gravitational waves than standard inflation, offering a potential path to distinguish between them. Small deviations from perfect isotropy in the CMB, or the presence of specific non-Gaussian features, could also hint at a previous cycle. The cyclic multiverse hypothesis, born from the sophisticated mathematics of brane theory, paints a dramatic picture of an endlessly reborn cosmos. It transforms our Big Bang from a unique creation into a periodic event, a rhythmic pulse in an eternal cosmic dance. This perspective not only addresses deep philosophical questions about ultimate origins, but also provides a framework for how different universes, with potentially varying laws, could emerge not just in parallel, but sequentially over unimaginable timescales. It's a universe that refuses to have a single beginning or a final end, forever renewing itself through the grand, unseen mechanics of higher dimensions. From the vast, unobservable reaches of an infinitely stretching cosmos and the cosmic collisions of branes, we now turn our gaze inward, to the most intimate and perhaps most challenging multiverse hypothesis, the just quantum branches. Often known as the many worlds interpretation, MWI, of quantum mechanics. Unlike previous multiverse theories that rely on cosmological expansion or extra dimensions, the many worlds interpretation springs directly from the perplexing nature of reality at its most fundamental scale, the quantum realm. At the heart of quantum mechanics lies the principle of superposition, which states that a quantum particle can exist in multiple states simultaneously until it is observed or measured. Before observation, a particle's existence is described by a wave function, a mathematical entity that encodes all its possible states and their probabilities. But what happens when we observe it? The wave function collapses, and the particle settles into a single, definite state. This collapse, however, has always been a source of deep philosophical and scientific unease, often referred to as the measurement problem. The many worlds interpretation, proposed by Hugh Everett III in 1957, offers a radical solution. The wave function never truly collapses. Instead, every time a quantum measurement is made, or every time a quantum event with multiple possible outcomes occurs, the universe splits, or branches, into as many parallel universes as there are possible outcomes. In each of these newly formed universes, one of the possible outcomes is realized. Imagine a simple quantum experiment, a photon striking a half-silvered mirror. It can either pass through or be reflected. According to MWI, at the moment of interaction, the universe splits. In one new universe, the photon passes through. In another, a parallel universe, the photon is reflected. Both outcomes are equally real, existing in their own distinct branches of reality. From our perspective, we only ever experience one outcome, the one that materialized in our particular branch. This branching isn't just limited to subatomic particles, since everything in the universe, including ourselves, is ultimately composed of quantum particles. Every decision we make, every interaction, every random event potentially triggers a branching of the universe. If you choose to turn left at a junction, in another universe, a copy of you turns right. If you miss a bus in a parallel reality, a version of you catches it and experiences an entirely different day. The implications are staggering. Every conceivable outcome of every event, no matter how small or large, is realized in some branch of this quantum multiverse. The beauty and the terror of MWI lie in its determinism. It removes the problematic concept of wave function collapse, asserting that the underlying Schrödinger equation, which governs the evolution of quantum systems, is always obeyed. Nothing is truly random or collapsed. All possibilities simply become actualized in different branches of reality. The observer effect in quantum mechanics is thus reinterpreted. It's not that observation causes collapse, but that the observer themselves become entangled with the quantum state and, in doing so, are duplicated across the branching universes. Each copy of the observer then perceives a different outcome. The branches of this quantum multiverse are not spatially separated like the bubble universes of eternal inflation. nor are they existing in extra dimensions like brain worlds. Instead, they are distinct, non-interacting realities coexisting in the same abstract mathematical space. They are parallel in the most profound sense, forever unaware of each other's existence once they have diverged. There is no possibility of communication or interaction between these branches. The concept faces intense philosophical debate. While it elegantly solves the measurement problem and is consistent with the linearity of quantum mechanics, it comes at the cost of an unimaginable proliferation of universes. The number of such branches would be astronomical, constantly increasing with every quantum interaction occurring throughout the cosmos. This many worlds interpretation implies an infinite, ever-growing tree of realities, where every quantum possibility blossoms into its own cosmic branch. The scientific challenge for MWI is its lack of direct falsifiability. By its very nature, the other branches are inaccessible to us. We can only experience our own branch. Therefore, there is no experiment we can perform, no signal we can detect, that would definitively prove the existence of these other worlds. Proponents argue that its strength lies in its conceptual simplicity and its ability to explain quantum phenomena without introducing arbitrary collapse mechanisms. Critics argue that it's an unnecessarily extravagant explanation, invoking an infinite number of unobservable universes to solve a problem that might have a simpler solution. Despite the debates, the many worlds interpretation remains a highly influential and actively researched area in quantum foundations. Its elegance in preserving the fundamental laws of quantum mechanics without ad hoc interventions makes it a compelling, if deeply counterintuitive candidate for describing the true nature of reality. It means that what if is not just a question of imagination, but a statement of actual existence. Every road not taken, every choice unmade, every possibility that flickered into existence for a moment is not lost but realized in a parallel, equally real universe. This quantum multiverse is a constant dynamic creation of new realities, driven by the very probabilistic heart of nature. It challenges our intuitive understanding of time, causality, and personal identity. If infinite versions of ourselves exist across these branching realities, what does it mean to be this version of me? It transforms our understanding of reality into an endlessly unfolding tapestry, where every quantum event adds new threads to the boundless fabric of existence. It is a multiverse born from the very equations that govern the smallest particles, yet blossoming into the grandest, most numerous of all cosmic possibilities. The dizzying array of multiverse hypotheses, from infinite emptiness to colliding brains and quantum branches, all converge on a single, profound philosophical crossroads: the anthropic question, why this universe? This query, often dismissed as mere speculation, forces us to confront the seemingly miraculous fine-tuning of our cosmos, where the fundamental constants and physical laws appear precisely calibrated for the emergence of complex structures and, ultimately, life. The multiverse offers a powerful, albeit controversial framework for understanding this cosmic, apparent luck. For decades, scientists have grappled with the observation that if many of the universe's fundamental parameters were even slightly different, life as we know it, indeed, even atoms, stars, or galaxies, would be impossible. Consider a few striking examples. The strength of the strong nuclear force which binds atomic nuclei is exquisitely balanced. If it were just a few percent weaker, stable atomic nuclei wouldn't form. If it were slightly stronger, hydrogen would have fused into heavier elements too rapidly in the early universe, leaving no hydrogen to fuel long-lived stars like our Sun. Both scenarios preclude the existence of complex chemistry necessary for life. Similarly, the ratio of the electromagnetic force to the gravitational force is crucial. If electromagnetism were marginally stronger, stars would burn too hot and too quickly. If gravity were slightly stronger, stars would collapse into black holes too readily, or the universe itself would have collapsed long ago. Even the precise value of the cosmological constant, the elusive dark energy driving cosmic acceleration, appears remarkably fine-tuned. If it were much larger, the universe would have expanded too rapidly for galaxies to form. If it were smaller or negative, the universe might have recollapsed. Our universe exists within a narrow life-permitting window of these parameters. This apparent fine-tuning has historically been interpreted in two main ways. One view suggests an intelligent designer, a cosmic architect who meticulously crafted the universe for a specific purpose. This theological perspective, while comforting to some, falls outside the purview of scientific inquiry, as it offers no testable predictions. The second view attributes it to extraordinary cosmic luck, an incredibly improbable roll of the dice where our universe just happened to hit the jackpot. While statistically possible, such an outcome feels deeply unsatisfying to many scientists. This is where the multiverse enters the debate, offering a scientific, albeit indirect, explanation through the anthropic principle. The anthropic principle, in its various forms, essentially states that the conditions we observe in the universe must be compatible with our own existence as observers. It's not that the universe was designed for us, but that we can only exist in a universe that allows for us. In the context of the multiverse, the anthropic principle takes on a statistical interpretation. If there is an infinite ensemble of universes, whether spatially separated, level 1, arising from eternal inflation with varying laws, level 2, or branching through quantum events, level 4 as Tegmark would classify it, then it becomes statistically inevitable that some subset of these universes will possess the specific, life-permitting parameters we observe. We, as observers, simply find ourselves in one of these habitable universes by selection effect. It's like finding yourself in a room where the air temperature is precisely 20 degrees Celsius. If you knew there were only a handful of rooms in existence, it might seem miraculous. But if you knew there were an infinite number of rooms, each with a randomly set thermostat, then finding yourself in a comfortable one is not surprising at all. You could only exist to observe a comfortable room. This multiverse solution transforms the fine-tuning problem from a mystery, requiring divine intervention or incredible luck, into a natural consequence of cosmic abundance. Our universe isn't special in its fundamental design. It's just one of the rare ones that supports complexity and consciousness. The vast majority of universes in a level 2 or level 4 multiverse would be barren, sterile realms where atoms don't form, stars never ignite, or life is an impossibility. We simply don't observe those universes because no observers could arise within them. However, the anthropic principle, even when applied to the multiverse, is not without its critics. Some argue that it is a tautology, merely stating that we exist where we can exist, offering no predictive power or deep insight into fundamental physics. Others worry that it could become a cop-out, a way to avoid seeking deeper physical explanations for the fine-tuning. If any anomaly can be explained by another universe does it differently, then it potentially undermines the scientific quest for a single, overarching theory of everything. Despite these criticisms, the anthropic principle remains a powerful conceptual tool in the era of multiverse theories. It provides a logical bridge between the vast, seemingly improbable cosmic parameters and our very existence. It suggests that the laws of physics we measure are not necessarily universal laws of all existence, but rather the specific manifestations of physics within our particular cosmic reality, a reality selected by the very fact of our sentience. The search for indirect evidence for a multiverse, therefore, becomes a quest to either confirm the anthropic selection or to find an underlying physical principle that truly explains the fine-tuning within a singular universe. Until then, the multiverse provides a compelling, if unprovable, answer to why our cosmic home seems so perfectly suited for us, transforming our singular perspective into a statistical likelihood within an unimaginably diverse cosmic ensemble. It asks us to accept that our universe is not the exception, but simply one of the few possibilities in a vast self-selecting cosmic lottery. The grand tapestry of multiverse hypotheses, from the endlessly repeating to the brain-bound and quantum branching, ignites a crucial question. Can any of this be proven? How does science, grounded in observation and testable prediction, grapple with realms that are, by their very definition, beyond our direct reach? The answer lies in the subtle art of hunting for multiverse footprints, searching for whispers from beyond our cosmic horizon that might betray the presence of these hidden realities. For the level 1 multiverse, an infinitely stretching version of our own cosmos, direct proof remains elusive. By its nature, the other universes are simply too far away for their light to ever reach us. However, the theoretical robustness of an infinite flat universe, as supported by observations of the cosmic microwave background, provides indirect support. If future, more precise measurements confirm the universe's flatness with even greater certainty, it strengthens the case for this boundless expanse. Yet, confirming the statistical repetitions of identical Earths remains a philosophical extrapolation, not an empirical test. The search intensifies for the Level 2 multiverse, born from eternal inflation. If our universe is a bubble in a larger inflating metaspace, could its birth have left an imprint? One tantalizing idea involves cosmic collisions. If our bubble universe once collided with a neighbouring bubble in the metaspace, the impact might have left a distinctive bruise on the cosmic microwave background (CMB). This bruise could manifest as a large-scale statistical anomaly, a region with an unusual temperature or density fluctuation that cannot be explained by the standard Big Bang model. Scientists are meticulously scanning the CMB maps from missions like Planck for such non-Gaussian features or anisotropies that might betray the ghost of a past collision. While no definitive evidence has yet emerged, the search continues, representing a direct observational avenue for multiversal detection. Another potential footprint for eternal inflation lies in the gravitational wave background. The inflationary epoch is predicted to have generated a stochastic background of primordial gravitational waves, ripples in spacetime itself. Different models of inflation, including those leading to eternal inflation and the Level 2 multiverse, predict distinct signatures for these waves. Detecting and characterizing this gravitational wave background, perhaps through future space-based interferometers, could provide crucial insights into the physics of inflation and, indirectly, the multiversal landscape it generates. Deviations from the expected spectrum of these waves could point to more complex inflationary scenarios, like those inherent to a bubbling multiverse. For the brain-world hypothesis, where our universe is a membrane in a higher dimensional bulk, the hunt for evidence focuses on extra dimensions and the behavior of gravity. If extra dimensions exist, even if compactified or inaccessible to most forces, they could manifest in several ways. LHC are constantly searching for exotic particles that might escape into extra dimensions, or for tiny deviations in fundamental force laws that would only arise if gravity were leaking away from our brain. The detection of micro-black holes at energies lower than expected, or subtle changes in gravity's strength at very small distances, the inverse square law might break down at submillimeter scales, could be a powerful indication of extra dimensions. While the LHC has so far found no definitive signs, these experiments continue to push the boundaries of energy and precision, directly probing the space where extra dimensions might reside. The most dramatic yet elusive evidence for brain worlds would be brain collisions, as discussed in the cyclic multiverse models. Such events would generate incredibly powerful gravitational waves and potentially leave unique signatures on the CMB that differ from those predicted by bubble collisions. The challenge is distinguishing these faint, specific signals from the noise of standard cosmological processes and observational uncertainties. It requires exquisite precision in our cosmological measurements and advanced theoretical modelling to disentangle genuine multiversal imprints from mere statistical flukes. A Level 3 or a V multiverse, depending on classification, presents the greatest challenge for empirical verification. Since its branches are causally isolated and constantly splitting, there is by definition no way for us to interact with or observe these parallel realities. Our experience is inherently confined to a single branch. Therefore, scientific proof for MWI often relies on its philosophical elegance and its ability to resolve the quantum measurement problem without introducing arbitrary collapse postulates. However, some theoretical physicists are exploring whether quantum coherence experiments, pushing macroscopic objects into superposition, could indirectly hint at the reality of these branching states. These are highly speculative avenues, pushing the very definition of what constitutes scientific evidence. Ultimately, the quest for multiverse footprints is a testament to the scientific method's relentless pursuit of truth, even when faced with seemingly intractable problems. It's a journey into the unknown, driven by the belief that even the most exotic theoretical constructs might leave subtle, detectable whispers in our observable reality. Whether through anomalies in the CMB, the detection of primordial gravitational waves, or minute deviations in gravity's behavior, scientists are meticulously sifting through the cosmic data, hoping to find that single, unmistakable clue that transforms speculation into established fact. Until then, the multiverse remains a stunning testament to the ingenuity of theoretical physics, expanding our minds to possibilities far grander than our single perceived universe. The search continues, ever pushing the boundaries of what is known and what might yet be discovered just beyond our current cosmic grasp. Our intellectual odyssey has taken us to the very edge of the observable cosmos and plunged us into realms beyond imagination. We began by acknowledging the arbitrary nature of our cosmic horizon, a boundary of light and time, not a physical wall to existence. From there, we dared to contemplate the simplest, yet profoundly unsettling possibility, an infinite emptiness, a boundless expanse of our universe stretching forever, where the laws of physics remain constant and the sheer mathematics of probability dictate the infinite repetition of every cosmic configuration, including countless copies of ourselves, living out identical lives on myriad Earths. This Level 1 multiverse compels us to confront the idea that our personal narrative, our very uniqueness, might be just one iteration in an endless cosmic series. We then ventured into the more dynamic and fertile landscapes of the eternal inflator, a mechanism born from the very earliest moments of our universe. Here, cosmic inflation, instead of ending uniformly, perpetually bubbles off new universes from an ever-expanding metaspace. These bubble universes, the Level 2 multiverse, are causally disconnected, each a distinct space-time with its own Big Bang and, crucially, its own unique set of fundamental constants and physical laws. Imagine a cosmic foam, where each bubble is a self-contained reality, perhaps with different strengths of gravity, different masses for elementary particles, or even a different number of spatial dimensions. This vision offers a powerful, albeit indirect, solution to the fine-tuning problem, suggesting that our life-permitting universe is not a cosmic miracle, but simply one of the few habitable outcomes in an infinite cosmic lottery. The journey continued into the intricate architecture of our brain cosmology, a cornerstone of string theory and M theory. This paradigm challenges our three-dimensional intuition, proposing that our entire universe is a brain, a cosmic membrane, embedded within a higher dimensional bulk space. In this scenario, gravity, unlike the other fundamental forces, is free to traverse these extra dimensions, accounting for its perplexing weakness in our perceived reality. The existence of a bulk immediately opens the door to colliding realities, where other parallel brains, other universes, float alongside our own. These titanic, unseen interactions could be the very genesis of new Big Bangs, leading to cyclic multiverse hypotheses, where the universe is not born once, but eternally rebounds through phases of expansion and contraction, each cosmic rebirth potentially altering its fundamental parameters. It is a universe without a true beginning or end, forever caught in a cosmic dance of destruction and creation. Finally, we turned of multiverses, the quantum branches, embodied by the many worlds interpretation. This theory, stemming directly from the perplexing nature of quantum mechanics, posits that quantum measurement, every probabilistic event, causes the universe to split into multiple parallel realities, each representing a different outcome. In this continually branching quantum multiverse, every conceivable choice you could make, every path not taken, every possibility, is actualized in some parallel reality. It forces us to redefine not just the universe, but the very nature of reality, observation, and our own subjective experience within an endlessly proliferating cosmic tree. These diverse hypotheses, though profoundly different in their mechanisms and implications, collectively shatter the antiquated notion of a singular, isolated cosmos. They move beyond the simple expansion of our observable bubble to a grander, more complex understanding of existence, where our universe is merely a component, a single thread in an unimaginably vast cosmic tapestry. The central question from our hook, what lies beyond that cosmic horizon, is no longer met with silence, but with a cacophony of theoretical possibilities, each more awe-inspiring than the last. The philosophical weight of these multiversal scenarios is immense. If true, they challenge our understanding of fundamental laws, replacing universal constants with local parameters. They shift the fine-tuning of our universe from an improbable stroke of luck to a statistical inevitability, profoundly altering our perspective on humanity's place. We are no longer necessarily at the centre of existence, nor even in the only existence. Instead, we are but one conscious observer in one universe, among an infinite or near-infinite collection of realities. This realization can be both humbling and exhilarating. It diminishes our cosmic uniqueness, while simultaneously expanding the very concept of what is. The scientific quest for multiverse footprints remains one of the most exciting and challenging frontiers. While direct travel or communication with these other realms is likely impossible, the search for indirect evidence continues. Anomalies in the cosmic microwave background, specific signatures in the primordial gravitational wave background, subtle deviations in gravity's behavior at tiny scales, or the elusive detection of particles escaping into extra dimensions. These are the faint whispers we listen for. These theoretical predictions, however speculative, transform the multiverse from pure philosophy into testable science, pushing the boundaries of what our telescopes, particle accelerators, and minds can perceive. Even without definitive proof, the mere conceptualization of these multiverses expands our understanding of the universe's potential for diversity and complexity. Ultimately, the journey beyond the universe is a testament to humanity's insatiable curiosity and its capacity for abstract thought. From ancient myths of celestial spheres to modern theories of cosmic inflation and brain collisions, our quest to understand where we are and what else might be has continuously reshaped our worldview. The universe, once a simple dome overhead, then a vast galaxy, then an expanding cosmos, now stands poised to become a single member of an infinite family. This progression, from the geocentric to the heliocentric, to the galactocentric, and now potentially to a multiversal-centric view, embodies the very essence of scientific progress, a constant re-evaluation of our place in an ever larger, more intricate reality. We stand at a pivotal moment in cosmic history, where the fundamental questions about the nature of existence are being reframed by cutting-edge physics. Are we truly alone in our cosmic bubble, or are we surrounded by a boundless sea of other universes, each a unique expression of physical possibility? The answer, if it ever arrives, will undoubtedly redefine our understanding of everything. Until then, the multiverse hypotheses invite us to ponder not just the infinite possibilities within our universe, but the infinite possibilities of universes themselves. What deeper truths might lie in the unobservable, the unexplored, the realities that stretch beyond our wildest dreams. The universe, in all its grandeur, continues to be the most profound mystery, and our journey to comprehend it has only just begun.